All right, the second half of Module 7 is we're just going to run you through a whole bunch of tools that you can use on DEMs and expose you to about everything we can think of. The PowerPoint's going to be a little disjointed because I'm just going to run through the tools in a disconnected way, just so you can kind of see what they are, what they mean, how they might look, to expose you to that. How is this feeling? Is this ringing true for you guys at this point in the semester? I know this class is a lot of work and we really expose you to a lot, but hang in there. This is a fun lab, even though it's a little bit piecemealy. I don't know, just enjoy, I guess. Okay, so the first thing I want to talk about is that there are two basic types of rasters. You can have an integer raster and a floating point raster in the most general sense. The big difference, and the reason it's important to point this out, is integer rasters. This is a table of contents with three different raster types. We've got a reclassified, where you create either a binary raster with zeros and ones or ones and twos or something like that. But the point is, this is an integer, and it creates an integer raster. And you can build an attribute table with integer rasters. They have a limited number of values that can exist, and so it's possible to display that in an attribute table. On the other hand, typical DEMs are floating point, which means they have decimal places here. There are so many possible values here that if you tried to open the attribute table in the table of contents, you'd see it grayed out. ArcMap does not create attribute tables for floating point rasters. This is just an important differentiation. So here's a hillshade for this DEM. And we know from hillshades that it's just a series of bins, and these bins are integer files. So a hillshade raster is an integer file, and therefore it does have an attribute table. You can see here there's 255 records, and that's because there's 255 bins in this color ramp. So the count here is what I want to get at. In a hillshade, the count isn't very important. It means there are this many cells that have the value of 0. This is black. And if we scroll down, we'd see that there are a certain number of cells with the value of white. This is very important in a binary raster. In a binary raster, what you've done here is, I'm assuming this is a slope raster that's been reclassed to take into consideration slopes greater than 45 degrees. So the true areas are areas on this surface where the slope is greater than 45 degrees. And if we wanted to know what that total area was, we can calculate that from the count. The count tells us how many cells have slope greater than 45 degrees. We also can determine what each cell size is from the resolution. And from that, we can calculate the area, and we're going to do that right now. So number one would be just determining the raster cell size. And in the most basic way, you could just zoom way on in to see the individual pixels of your raster, take your measure tool, and measure across the width of a cell. And here you can see I got pretty close. You can also look in the raster properties in your table of contents, go to the source, and look at the cell size. It will tell you, how big each raster cell is. The units are associated with the coordinate system. So you just look down to the coordinate system and it would tell you it's probably meters. And we know that because we just measured it. Step number two is to determine how many cells there are. So again, we go back to that count. And we know that there are 345,926 cells that have slope greater than 45 degrees. Step 3 is to multiply the number of cells by the cell area to get the total area. Let's say it's in a watershed, and we want to know what the total area of southern aspect is. The total number of cells by the cell area will give you the total area for any cell value. So in this case, this is our number of cells multiplied by the area of each cell gives you a total area. You can convert it to whatever units you find are appropriate. Pretty straightforward. All right, zonal statistics. This is a very useful tool. Let's say you have some sort of input surface. In this case, it's a slope raster. And then you have some zone. You could use watersheds. You could use polling districts. You could use state boundaries. Some zone that you want to summarize a statistic for. So in this case, we're going to use slope. And we could output what the average slope is, what the maximum slope is, what the minimum slope is for our watershed. You could use multiple watersheds and summarize slope. You could also use anything you want in here, aspect, any kind of surface raster you could summarize this way. So one way to do it is to use the straight zonal statistics tool. It outputs a polygon shape file that matches your input, your zone. and it gives you one statistic, and you can pick what this is. In this case, I picked mean slope, but you could do maximum, minimum, standard deviation, whatever you want. You can also run zonal statistics as a table, and this doesn't output a shapefile, it just outputs a table, obviously, but this way you can calculate all statistics at once and not just do one. So this is great for display, but if you really are going after the nitty-gritty, it'll calculate the area for you and then give you the mean slope, the max slope, the range, the mean standard deviation. So that's zonal statistics. Another tool you're going to run in this lab is interpolation, and you probably have a sense of what this is. It's basically being able to create a raster or continuous surface from discrete points of data. So these could be weather stations or rain gauges, or it could be your research site where you're looking at species diversity, and you have known sample locations with known values. And what you want to do is create a continual surface of data across that same area. That's the method of interpolation. We're going to use inverse distance weighted. There are a lot of different ways to interpolate and predict values across a raster. I challenge you to dig into this a little bit if you're curious, or if your research calls for something like this, we can talk about it individually, but just so that you get an idea of how to run tools like this, we're just going to run the IDW tool and interpolate rainfall over an area. Reclassify. You're going to do this a ton this semester for a lot of different reasons. So it's a really helpful tool. So in that first example I showed you, we created a binary raster of kind of true-false whether slope was greater than 45 degrees. So our input raster is going to be a slope. This time slope has been calculated in percent. And what it does is it brings in the classification that it assigns in the table of contents. We could go through and manually change these to have slopes. Let's say we want 10%. We could go through and manually change all these numbers, or cheat, press this classify button. That opens a classification window. You could change the classes to 2. This is an ARC glitch where you have to actually change the method away from manual, change it to equal interval just temporarily. That allows this to activate, and then you can change the classes to 2. You don't need to change this back. If you go and type over this first number, let's just say we want our classes to be 0 to 10 and 10 to the maximum. If you overwrite 10 here, leave the maximum in there and click OK, it simplifies the reclass window just that. So we have now 0 to 10 as 1, and we can make a binary raster and take all other slopes, higher slopes, and assign them to 0. This is a traditional binary raster. The output's going to look like this, where you have for every single cell a true or false. The blue areas are the true, where the slope is less than 10%, and the purple are the higher areas, where slope is greater than 10%. These can be useful. Binary rasters can be useful, especially if you're going to stack a bunch of different rasters and do kind of a composite. But I find it's more helpful for the stuff that we're going to be doing to actually write off and get rid of the false. And I'll show you why this is helpful in a second. So we're going to maintain true for our low slopes, and we're going to change the higher slope class to no data. This actually makes it go away. The output looks like this. So the blue is the true area. Notice the purple's gone. What you see, all the green underneath here, is just the slope raster that the reclass was done on. So the green and orange background is just a backdrop, but you can see that you can see through it now. And now the true areas are left, but everything else has actually disappeared. And this is why that's really important. We can convert rasters to polygons. So let's say we wanted to know which of these areas was big enough to build a house on. And we wanted them to be 2 acres in size or something like that. We wanted it to have low slope, and we want to be able to build a campsite or something there. In order to calculate the areas of these little pods, we need to convert them to polygon so we can calculate the geometry on them. We can't use the calculating area tool that we did at the very first slide because these all have the same value, so our count would be all of this together. There's no way to break them apart into little chunks. We can do that if we convert it to a polygon. So we're going to run the raster to polygon tool, and we input our reclass, so where we have our 1s, and run this, and this is the output. So you can see the dark blue raster behind it, and because we simplified the polygons, it does just that. It kind of simplifies those shapes. If you didn't simplify it, you would get a polygon with this checkerboard raster. It would exactly match the raster cells. The thing to know about doing a raster to polygon, I haven't quite figured this out yet, but sometimes when you run the raster to polygon, The output is one record. Even though there's individual polygons sitting in here, it all comes in as one record. So if you were to highlight this record, it highlights every single little polygon in that shapefile. Sometimes, like in our case, we want to know the area of each individual polygon, so we need to break these apart into their own records so we can calculate the area on each one. And to do that, you run a tool called Explode Multipart Feature. It's in the editor toolbar. You have to start an editing session. This is the editor toolbar. You drop this down, start editing on this polygon. And then you can explode to multipart, which is this tool right here, Explode Multipart Feature. Click this, and the results are, you can see that the attribute table now has gone from one record to 7,000 records. So each one of these polygons has become its own record in the table. Notice that the shape area has not been updated. So the area overall is this, and I'm assuming this is meters squared. I always like to put my units up here when I calculate area. But now that this needs to be updated, so in this attribute table you would just right-click, calculate geometry, and it would update the areas for all these little polygons, and then we would know which one of these shapes is greater than whatever our requirement it is, whether it's 2 acres or whatever it is. Okay, that's Explode Multipart Feature. We're almost done. Hang in there. So focal statistics. This is a really awesome tool. It's an algorithm that sweeps across the raster cell by cell, and depending on the neighborhood that you're using, both the size and the shape of it, and then the statistic that you're calculating, this algorithm sweeps over the whole raster, and for every single processing cell, the center cell, it creates an output based on the window and the statistic. For example, here we have a 3x3 moving window, 9 cells, and we want to calculate the sum. So we've got 9 cells, we sum the cell values, and the output for this processing cell is the sum of that neighborhood. Where this gets really cool is you can make this any size window you want, any shape you want. It can get really funky. This could be something that you would do for, let's say you have a land cover raster with just numeric categories representing vegetation type. And you want to get at the diversity of vegetation types for any given area. So you could make this a 3x3, 5x5. You could make it a 1 kilometer moving window and look at variety. So the different statistical outputs you can calculate, variety is one of them. So for the output cell, or the processing cell, it's going to look at how many different types of vegetation are found within this window, and the number of types, or the variety, is output. You might also want to know what's the dominant vegetation type in your window. And it would just look for the majority. So how many, here we have a tie between 3 and 4. So it would get at the majority of land cover. And then you could map, you would map this based on your majority type or your statistic type. So again, the neighborhood shape and size and the statistic type are both variables that are set by the user. Okay, last one. Distance functions. This is a very simple tool, and it also can be made very complex. We're going to run the most basic distance function, which is a Euclidean or straight line distance. But know that you can also make cost-weighted distance rasters, where you take other factors into consideration as a cost that goes into your distance measurement. So how steep the slope is, or what type of land cover. Fire departments can use this for using traffic. They can calculate the fastest distance between their location and the fire and take construction and traffic into consideration as a cost. But what we're going to do is just run a basic straight line distance tool. Maybe you have some sort of requirement that you can't be more than 10 miles away from a donut shop at any given time. So you could take a point file map of donut shops and create a Euclidean distance map that shows you from any place. Maybe you've got this on your phone. You know that if you're in a yellow zone, you are outside your 10-mile comfort zone of being by a donut shop, and you need to actually relocate yourself. So that's what this type of output is. The tool also calculates the direction to the nearest source. So let's just say you are on the map and you're right here in this light green area. It's telling you that you need to travel east to get to the closest donut shop. So if you start walking east and all of a sudden find yourself in the orange, if you walk northeast, that's the direction to go to get to the nearest donut shop. In combination, they might be useful, they might not be useful, but this is what you're going to be doing for the last step of this lab. There are a bunch of questions to answer, so you'll be submitting a text document and one formal map just to get some practice using multiple data frames. And don't spend a lot of time on this. Basically just a snapshot of your distance analysis that you're submitting. And that's it. Have fun.